All right. Well, hopefully everybody did a good job working with the um, hypothesis test and being able to prove whether the regression line was significant or not significant. So all this work that we've been doing really comes to this section here. So because this is really the reason we want to be able to do linear regressions is to be able to model data based on certain information. So for example, with mine, with the house price is the one that I've been working on. So the goal is I'd like to be able to have a way to say, okay, well, here's a 3,500 square foot house. What should be the approximate selling price for this house? If I was a real estate agent or if I was an appraiser or something like that, it'd be nice to have some kind of a formula to be able to use. And so that's really the goal of using linear regressions to begin with. So in this case, let's just jump right in because there's nothing really new to learn. And if you remember from algebra, like this is just a lot of algebra type stuff. So in this case, this is my linear regression equation. I think I found in 12.3. So I did round it off a little bit just because it was a little bit too big. And you'll probably want to do the same thing. I mean, unless you're using your calculator or Excel or something, you probably don't want to keep as many of those digits around as possible anyway. So what we're doing is that they're going to give us the input value. So in this case, like our x, and our goal is we're trying to find the y hat, the approximate value based on this regression line. And so what we're going to do is just go ahead and plug in 3,500 for x. So 0.099 times 3,500 plus 160.23. And now we just kind of plug this in the calculator for y hat. 0.099 times 3,500 plus 160.23, and we get $506,073 in this case, so 506.73. And so remember, this means this is in terms of thousands. So the idea is, like, if I want to write this in words, I would just move this decimal point 3 places to the left. So in this case, we guess that a house 3,500 square feet will cost $506,730 in this case. So again, we're just making an estimate, a good estimate, because we saw that our regression line with this is significant. So that means that we can use it. It's fairly accurate, which is kind of nice. So now let's do the same thing. So predict the price of a home that is 6,000 square feet. So again, same idea. So y hat equals 0.099, 6,000 plus 160.23. So again, let's throw this in the calculator and see what we get. Let's change this to 6,000. And so now we get 754.23. All right, so 754.23. So again, same idea. So a 6,000 square foot house should cost 750. What is that? The ugliest five ever. $754,230 in this case. So if you notice, and we're going to talk about in the next section here. So one of the data points that was chosen, the 3,500, is in the range of these values. So, or pretty close. So actually, I guess it's even a little bit bigger. So that was my bad. I guess I should have picked one that was smaller. So that was dumb. But so the goal is there's two different ways you can talk about these regression lines. There's interpolation and there's extrapolation. So unfortunately, what I've done is both of these guys are extrapolation because the values are outside of the original data set. So our original data set ran from 2,521 square feet up to 3,198 square feet. So the goal is, since the model, the line was based on those values, then if you're interpolating data using values that are sort of in between those X values, then you probably are going to get a better estimate than if you go either above the data or below the data. So if you're in this area of the graph, this would be interpolation. And so if you go above or below, then those are going to be extrapolations. So again, you can still use the line or try to use the line, but you have to be careful, because if you're in those upper areas or lower areas, since no data was actually used to predict that line, there's no guarantee that these predictions are going to be very good. So unfortunately, I picked two of them that are up in this area up here, which was not my goal. So I mislooked at the data. So sorry about that. But that's kind of the thing you want to look at. So just be mindful of, when you're extrapolating data, that it may not be as accurate as if you're interpolating data. So just kind of keep that in mind. And so that's what this little paragraph talks about. It just kind of gives you a little bit of a warning about that. So to be mindful of that. All right, so let's go on to how else we can use this data, or the regression line, as a way to predict data. So another thing that we can do is what's called interpreting the slope. So we can make predictions by considering just the slope alone and what effect it will play on the data. So in this case, if the difference of the X values of two data points is 1, so for example, like maybe we had X equals 35 and X equals 36. So at this point, we're just talking about the X values. Then their Y values will differ by the amount of the slope. So in this case, in other words, if you take x2 minus x1 and it equals 1, then y2 minus 1 is actually going to be equal to the slope in that case. But if the difference of the X values of two data points is 2, so say in this case we had like X equals 35 and X equals 37, so their difference is 2. Well, now the difference is going to be twice the amount of the slope. So instead of just getting A, in this case we're going to get 2A as our calculation. And in general, if you go any amount possible, so if there's n difference between these guys, then you're going to take n times the slope. So if the difference is 5, then the difference between the y values is going to be 5 times the slope. If the difference is 100, then the difference in the y values is going to be 100 times the slope in this case. So let's do this example 2 to make a prediction about the house prices. So in this case, two houses differ in size by 400 square feet. How much would you expect their prices to differ? So in this case, that 400 is actually the x2 minus x1, which equals my 400, or another way to think about it, my n in this case is going to be 400. So that means my difference in y values is going to be y2 minus y1 equals 400 times the slope. So it's going to be 400 times the amount of the slope, and our slope was, because this is the same problem, so 0.099. So if we throw this in the calculator, so we see that there's going to be 39.6 is going to be the difference. So our difference in our y values should be 39.6. But again, if we want to think of this in real world terms, think about moving this 2 places to the right, or 3 places to the right. There we go. Then what we're saying is that if the square footage differs by 400, the prices, or the price, will differ by 396 or $339,600 in this case. So basically, the bigger house should be worth $396,000 more than the other house. So it's not the cost of the house or anything like that. It's just the difference between the two houses. All right, is that okay with everybody? All right, perfect. So now let's look at interpreting the intercept. How can we use the intercept as a way to interpret data? So we can do the same thing for the intercept. So remember, just recall the intercept, or in particular, in this case, the y-intercept is the point for which the line crosses the y-axis. So in other words, this will be the point where x equals 0 for some y value. Therefore, when we want to use the intercept as a way to make a prediction, we need to first be sure that, that should be x equals 0, even makes sense in the context of the problem. We know because we have an equation, we can, of course, let x equal 0, we can get an answer, but that doesn't necessarily mean that it's going to give you good data. So just because we've got an equation and we can plug 0 in, first off, doesn't mean that x equals 0 is realistic and can even happen. And second, the output value you might get might make 0 sense whatsoever in this case. So let's look at some examples of these so we can see if the intercept even makes sense. So for my problem, so again, this is the house problem. Interpret what it would mean in the price of houses based on the square footage example. Does the intercept make sense in this example? So again, just to write my equation down again, so I've got it here. So y hat equals 0.099x plus, what was it, 160 something, 60.23. So first off, if I let x equal 0, what's that mean in relationship to my problem? Then that means that the house I want to buy is 0 square feet. So first off, I don't know anybody that would really want to live in a house that was 0 square feet, because that would basically mean there was no house whatsoever there. So, I guess theoretically, you could relate it to that's how much the land would cost or something like that. But so in this case, I would say mine doesn't really make any sense, because if the goal is to buy a house, not just a piece of land, so in this case, we're assuming there's a house on the property, then in this case, my example doesn't even make any sense. And even if it did, if I put in 0 into this equation, then this would give me a y hat of 160.23. So again, if you wanted to buy a house that was 0 square feet, you'd have to pay $160,230 for it, which seems a little ridiculous to buy a house that doesn't even exist. So mine kind of doesn't make sense on lots of levels. But again, that's what you have to think of when you're trying to use the intercept to see if it makes sense or not. So practice 1 is having you guys go through, kind of looking at some different examples, see if you can figure out whether the intercept makes sense or doesn't make sense for the given problems. So give your reasons why. Practice 2, so again, this is doing the same thing you guys have been doing with the same examples, going through, trying to figure out, the y-intercept and stuff like that, kind of testing some different values. And same thing for practice 3. So when you're done with this, come on back and we'll finish the last section of the semester. Woohoo!